Hello everyone and welcome to this video presentation on Seismic Hazard Assessment of Nepal in NBC 105-2020. As the revised building code on seismic resistant design of buildings in Nepal NBC 105-2020 has been approved by the government of Nepal, this video presentation will talk about the seismic hazard section of that code. It will talk about the methods that were used to arrive at the seismic hazard map that you see there, and also the design elastic response spectrum. So without further ado, let's begin. So what is the purpose of seismic building codes? Every building codes out there attempt to answer this main question to the structural engineer: what load should I take to design my structure? So let's recall Newton's second law of motion, that force equals mass times acceleration. Rearranging this term, multiplying and dividing by acceleration due to gravity, we get the force experienced by a structure at its base is equal to its weight times a coefficient, and this coefficient is termed as base shear coefficient. It is the ratio of seismic acceleration intensity at the base of the structure to acceleration due to gravity. Usually, this is expressed in terms of percentage of building weight, which is a sum of the dead load and a fraction of live load. So, to estimate the seismic demand, we need two quantities, which are seismic weight and base shear coefficient. If you compare the uncertainty between the two, then base shear coefficient is very uncertain, for which we need a reliable method of estimation. This is usually done by probabilistic seismic hazard assessment. Okay, now let's call the probabilistic seismic hazard assessment as PSHA throughout this video. Well, and it's not easy task to explain this on few slides. If you want, then I can dedicate an entire video series for PSHA. But today I'll try to illustrate it in few slides, explaining you all the key concepts behind it. So basically it has 4 steps. So let's say you are given a location to estimate seismic hazard. At first you identify the probable sources that can create seismic activities. For calculation purpose, these can be represented by a means of point, line, or an area. If it is by a point, then we call it point source, line source, area, then aerial source. However, keep in mind that this goes beyond the simple representation in the real industry. Engineering seismologists who conduct PSHA can model the entire 3-dimensional fault based on its tectonics and geological structure. Now that we have located our site of interest and identified the probable sources, it's time to consider a range of magnitudes starting from the lowest to the highest. Generally, magnitudes 4 or 5 are taken as the lowest because anything below that isn't significant in terms of the damage they cause to the engineering structures. And highest can be tricky because we have to understand the characteristics of the source, which can be influenced by a number of factors such as tectonics, past seismic activities, and others. Generally, assigning 8 is considered okay. Then after that, you plot the range of magnitudes considered in the x-axis and the frequency of occurrence of magnitudes greater than a certain value over a period of time. Natural logarithm is applied to this because the term in the y-axis varies from lowest possible value to highest, and taking log transforms this into a linear scale. Then perform linear regression to find out the coefficients a and b. Just to show you, if you take the log, then you will get the same thing in this form. I'm sorry, if you don't take the log, then you will get this form, which is a curve. So estimating the parameters for a straight line is a lot easier than for a curve. Once we are done with establishing the recurrence relationships or A-B values for each of the sources, then it's time we play with the probability. Because earthquakes are random things in nature, if you want to express them quantitatively, then probability is the tool we need. Just like we considered an array of magnitudes, apply the same concept to the distance as well. For example, a linear source can be discretized into smaller segments and the distance from each of the segment to the site can be calculated. Let's say 10, 15, 20 up to 200 kilometers. Then compute the probabilities associated with the magnitudes and distance. One thing interesting in the estimation of seismic hazards is that there are equations available that calculate the PGA given the magnitude and distance. These empirical equations are called ground motion prediction equations, or GMPE. These are developed for a reason you conduct PSHA, and if not available there, then you can borrow from the one that have similar tectonics. So given the distance and magnitude, we can calculate the corresponding PGA. So for the various combinations of magnitudes and distances that we talked earlier, we can compute the PGA like so. Also note that these GMPs are based on certain probability distributions. So you can calculate the conditional probability, say PGA exceedance by 0.1 g, given the distance and magnitude of 15 km and 4 respectively. Once we are done with computing the conditional probability, remember the recurrence relationships that we established earlier. We can plug in the values of A and B to find out the annual rate of exceedance of threshold magnitude, which in our case was 4. Now to find out the annual rate of exceedance of PGA, say 0.1 g, we multiply the annual rate of exceedance of threshold magnitude by the conditional probability we calculated earlier and its corresponding magnitude and distance. Then after that, we repeat this process for other combinations of magnitude and distance. Once we fill up the table, we sum up the contributions from each of the magnitude and distance, and this will give us the mean annual rate of exceedance of 0.1 g. Then we repeat this process for other sources as well and sum the contribution for a single PGA exceedance, say 0.1 g. And in the end, the process is repeated for PGA of a different range. For example, 0.01 g, 0.02 g, up to 1.5 g. So once we have computed the mean annual rate of exceedance for a range of PGAs, we can plot the PGA in the x-axis and mean annual rate of exceedance in the y-axis. When you have done this, we get a curve like so. However, as a structural engineer, we want to find out the probability of exceedance in the lifetime of the structure we want to design, say 10% probability of exceedance in 50 years. So this becomes a classic case of Poisson model for finite period. Once we know the probability of exceedance and design life of our structure, we can plug in those values in this equation, which for our case gives us an exceedance rate of 0.00211 or 475 years return period. Once we know the mean annual rate of exceedance, we can find the PGA from this curve. We've gone through this amount of detail to compute for a single site, so you can imagine the amount of computation that is done to prepare a seismic hazard map of a country, those found in the building codes. The computation is just immense and it's just too huge. So having given you the amount of background information, I am in a confident position to go further and explain you the process involved in the PSHA of Nepal. At first, as you can see, the earthquake catalog was procured from the Nepal Seismological Center and it was declustered, and a threshold magnitude of 4 was taken as discussed earlier. Then after that, this is just a plot of frequency of occurrence for different values of magnitude. So once we had gathered the earthquake catalog and declustered them, it was time we identified the seismic sources. These were based on seismotectonics, seismicity pattern, earthquake type and focal depth, and finally geological structure. Once we solidified the basis of source classification, we identified two main sources. These were subduction interface that runs from east of Nepal to the west and different aerial sources as shown. The 2015 devastating Gorkha earthquake caused significant damage and casualties, but it also provided an opportunity for seismologists to study the geometry of the main Himalayan thrust. So in the PSHA of Nepal, this identified three-dimensional geometry of MHT subduction interface was modeled as a single source. This was based on the works carried out by Elliott and others. And the other four aerial sources were northwest, northeast, northern grabens and southern source. The East Nepal has a strike slip deformation at depth 50 to 70 kilometers, while the northwest has depth of approximately 20 kilometers, and it also has a strike slip deformation type. I have to mention that in the earlier versions of PSHA that have been conducted in Nepal, there were no rationale behind the basis of source classification. The MHT was considered as the main source, but it was segmented into smaller sources. Here, a basis is provided for the source identification. So for the identified 7 sources, the recurrence parameters is like this. In the computation of the A and B values, there is a trend to calculate the A value based on B, which is fixed to 1. However, no such thing were done here. You can have a look at it. Then the GMPEs were applied in a logic tree format for the GMPE associated with the source type, giving equal weightage to each. So before showing you the hazard map of NBC 105-2020, let us go back to the 1994 version of NBC 105. This is a 300 years return period based map which has a maximum PG of 0.32 G, and this is located in the western and midwestern region. Kathmandu has a PG around 0.3 G. Now for the 500 years return period earthquake, the PGA has been increased to 0.42 G, and this has been concentrated in the far western and midwestern region. Kathmandu has a PGA around 0.36 G. And this is the zoning map of Nepal in the 1994 version of the building code. Surprisingly, the values are expressed in the form of coefficients rather than G. This had a major inconsistency issue, as it wasn't transparent enough to reveal the structural engineers the value associated with the intensity of ground acceleration. This created problems if one was to scale this for other use, such as performance-based earthquake engineering. Now, let's look at the results of the current PSHA. This is a hazard map at 10% probability of exceedance in 50 years or 475 years return period. In contrast to the earlier version, the isoseismal lines are not concentrated in certain regions that are mostly in the far west. And one thing to notice is that along the MHT, the hazard is very uniform, which has a return period, which at this return period has 0.4 G. Cities lying in this part experience more intensity, and as we move further up or down, the value decreases. Kathmandu has PG of 0.35 G, while Himalayan regions such as Jumla has only 0.26 G. And you must also have noticed that the difference lies only in the pattern, not with the associated values. Yet surprisingly, the base shear coefficients obtained in the previous version was rather just too low. Only 12% of the seismic weight if one was to design a moment resisting frame based hospital building in Kathmandu. So for this reason, time and again international communities have raised the question that seismicity in building code is just too low considering where it is located with regards to the seismic activity. This is at 2% probability of exceedance in 50 years. The pattern is similar in this case, with only the difference in the values, which is highest of 0.9 G along the MHT, and Kathmandu has 0.8 G. And this is the zoning map of Nepal shown in the current version, which is based on the 475 years return period. We've only simplified it a little bit so that it is easier to interpret for structural engineers. Okay, now the first part of the presentation is over and it has started to rain outside, and I'm sorry for the disturbance caused by it. We are done with the hazard part of the map, and now let's look how the hazard has been incorporated in the form of seismic demand. And before talking about that, about the revised code, let's talk about the seismic demand in the 1994 version. The base shear is expressed as the base shear coefficient times the seismic weight. The CD, which is the base shear coefficient, is a function of CT times zoning factor times importance factor times structural performance factor. So in order to find out the value of CT, you would have to look in the response spectrum curve, for which the corresponding time period you will have to calculate and look in the response spectrum curve. However, it had few problems. The first one being that the inconsistency in the format. All of these terms are expressed as coefficients, and you have no information about the seismic acceleration intensity at the base of the structure expressed in the form of PGA, or in terms of the acceleration due to gravity. And the next one is the value of base shear coefficient, which is pretty low as discussed earlier. So due to those inconsistencies, revised code has a new formulation that is entirely different from the former version. Now the CT equals ratio of spectral acceleration to PGA times PGA normalized by the PGA of 475 years return period times PGA of 475 years return period divided by G. It becomes clear that PGA of 475 years return period is the design basis earthquake, and this second term is related to the importance factor of the structure. Anything higher than 1 means we are designing for a return period greater than 475 years return period. So by this approach, we can scale to higher return periods. For example, this is very useful for performance assessment and performing nonlinear analysis. Now let's talk about the other two terms. The first term is called the spectral shape factor, and the last term is called the seismic zoning factor, which you see in the seismic zoning map. Likewise, these last two terms have been obtained from seismic hazard assessment, whereas the first term requires site response analysis because it deals with the shape of the response spectrum, which is a function of structural time period. As we have some background information about the PSHA and how it was conducted for Nepal, let's discuss about site response analysis. Structures are located at ground level, which is at a level above the engineering bedrock, and there can be different strata of soil, and these can act as a filter to modify the properties of ground motion recorded at the bedrock. They have the capacity to modify the intensity, duration, and ground motion frequency content. Since most of our engineering structures are built at the surface level, the analysis becomes very crucial in the derivation of design response spectrum. So in our case, one-dimensional site response analysis was performed. In the one-dimensional case, our soil column is broken down into many soil sublayers, and each of these layers is represented by unit weight and shear wave velocity. The input ground motion applied at the bedrock is assumed to travel vertically to the surface layer. So for this purpose, initial locations for site response analysis were identified based on the study in seismic risk of Kathmandu Valley carried out by JICA. The spectral shape factor available in building codes is a function of time period of the structure and type of soil. Mathematically, different layers of soil are represented by soil column as a multi-degree freedom system in one dimension. So stiffer systems have lower period and soil deposit is shallow, while flexible systems have longer period with deep deposit of soil. This concept was applied to classify the soil initially based on the time period of the soil column. And also note that the soil column is influenced by a number of factors. These include the total thickness of soil profile up to bedrock, dynamic stiffness of the soil profile, damping of the soil profile, impedance ratio between the soil profile and the underlying rock, the geological origin of strata that compose the soil profile, and variation of seismic site response characteristics as a function of the ground motion intensity. So these locations were identified based on the methodology discussed earlier. The deep deposits of Kathmandu Valley that have depth up to 500 meter is shown by the white circle in the map, and other soil types by the red circle. These were the initial points which were replicated elsewhere based on the similar geological profile. So if you are wondering what are the inputs required for the site response analysis, then these include shear wave velocity and Borel log profile, Number 2 is soil constitutive models. These include modulus reduction curve, damping ratio curve, backbone and hysteresis curve, which is required for nonlinear analysis only, and finally the input ground motion or acceleration time history. And please also note that everything was based on secondary data and information available at the time of analysis. The source is mentioned here. And these were the constitutive soil models for the respective soil types. And in order to consider the natural variability in ground motion, a number of ground motion, 20 in numbers, were considered from the NGA West ground motion database. You can see the mean of the selected ground motion is very close to the uniform hazard spectrum for the 475 years return period. If you are wondering what UHS is, then it is the PSHA done for other periods in addition to the zero period, which is the PGA. For the definition of spectral shape factor, this form was selected. The initial straight line is represented by the equation of a straight line followed by alpha, which is the plateau part between TA and corner period TC. Descending curve is represented by this equation. The displacement sensitive region is proportional to square of the time period, so this form was chosen. Now let's have a look at the results. This is a plot between the period and the spectral acceleration normalized by its PGA. The green line is the UHS at the bedrock, and this black line is the mean of the input ground motion. The ground motion at the surface after performing site response analysis is this gray line. This red line is the amplified input ground motion at the surface, and it is calculated as the ratio of the response spectra at the surface to the UHS at bedrock. So the influence of site response on the UHS is represented by this blue line. Finally, the shape factor defined earlier is fitted to this blue line. Based on that, the values of these shape factor parameters are determined. And for the other soil types also, the similar thing is done. So this is the spectral shape factor that you see in the NBC 105 2020. If we compare this with the earlier version, then a new soil type D has been added for Kathmandu Valley. In comparison to the other soil, the peak value of spectral acceleration is low for soil type D, which is the deep deposit. The results from the site response analysis in this type show characteristics that are consistent with the 2015 Gorkha earthquake. The new soft soil class in this revision has significantly higher spectral acceleration demand at longer periods, but at smaller periods it is less than other soil classes. This can be argued to be in contrast to the other international standards in which the seismic demand for structures of all natural periods is either equal to or greater for a softer soil category. And that was quite a long time. If you managed to bear with me, then I hope this has been very fruitful to you all. And before you leave, if this was useful, then please don't forget to hit and like the subscribe button, and please feel free to comment in the section down below. If you want to watch similar videos, then please do post the type of content that I come up with. Thank you all.